Ta-da! So I'm blanking out a little bit, but this is a nice paper that just came out in Nature that talks about how atmospheric rivers can produce extreme heat, especially in mid latitudes. Atmospheric rivers, if you don't know what they are, we define it right here. Atmospheric rivers are long, narrow bands of water vapor in the lower atmosphere that often lead to intense precipitation even at the poles. So you have to bring humidity even into the poles sometimes to create these uh, precipitation events, intense precipitation events, and obviously they can bring greenhouse effect, they can bring condensation heating, and there are other processes via which they can also create extreme heat. They also transport heat and energy to the Earth's surface, causing warmer winters and high temperature extremes in many regions. So this is a research briefing, which means the authors of the paper themselves provide a kind of a layperson's version of the summary. It's technical, but you don't have to read the whole paper if you don't want to, which tends to be much more technical. And I will just read the abstract and the conclusions from the main paper and show some figures. We'll read this part because this clearly explains what they are trying to do, and then it has an expert opinion that says what the significance of the work is, and then the editor puts in a blurb about why the paper was accepted, or some justification for why this is important work, right? So what is the project? Most of the moisture in the atmosphere is concentrated in the tropics, where warm temperatures and deep convection create towering thunderstorms and result in lush rainforests. To reach the mid-latitudes and polar regions, water vapor is transported in long, narrow regions of vapor known as atmospheric rivers. Although the extreme precipitation caused by these phenomena is probably well understood, there is no comprehensive understanding of how they affect local air temperatures. People have just looked at atmospheric rivers and precipitation even in the tropics, especially around California. I suspect that's where this terminology of atmospheric rivers actually started, California rain. This is a problem because the knowledge is important for determining, for example, the phase of the associated precipitation, whether it falls as snow or rain. To that end, we conducted a systematic global study to determine how and why atmospheric rivers affect near surface air temperatures worldwide, and whether they have a role in causing temperature extremes. That was the project. The observations, and then there is some implications that we'll look at. We used NASA's MERA-2 atmospheric reanalysis data set, which provides a self-consistent picture of the global atmosphere on an hourly time scale from 1980 to 2022 to investigate the relationship between atmospheric rivers and temperatures. So even though it's called the observation, it's a blend of model and observations. It's a dynamically interpolated gridded data that makes such analysis very possible. I wouldn't call them observations because they carry all kinds of issues that models have. You take a model, you integrate it forward, and you keep inserting data, and it doesn't conserve many things. There are many details, but nonetheless we keep calling them data sets, just as they do here, reanalysis data set. Is this strictly the correct way to do it? Well, we're just doing it anyways. So it allows them to do this analysis, the relationship between atmospheric rivers and temperatures. Because there is variation in the precise quantitative definition of an atmospheric river, we used a suite of 7 detection algorithms to identify atmospheric rivers across the globe. Using this robust set of identified features, we quantified the impacts of atmospheric rivers on surface temperatures and extreme heat events, and evaluated the physical mechanisms responsible for these effects. Our data were remarkably consistent even when using different methods to identify atmospheric rivers. We found that the atmospheric rivers cause warm air temperature anomalies, warm air temperature anomalies near the surface of the order of 5 degrees C above the climatological mean in the mid-latitudes and 10 degrees C or more near the poles. These warm temperature anomalies are largest in the winter season, so winters with more frequent atmospheric rivers are also warmer on average. Entire seasonal mean can go up if you have sufficient number of atmospheric rivers bringing in condensation of water vapor brought in from as atmospheric rivers. Just imagine that, okay? The main mechanism of this warming is the poleward transport of heat by atmospheric rivers in the lowest 3 kilometers of the atmosphere. Warming caused by this horizontal movement and convergence of heat leads to warming of the surface. This warming is bolstered by the large amount of water vapor in the atmospheric rivers, creating a transient enhanced greenhouse effect at the surface, increasing downwelling long wave radiation, although this is sometimes offset by the increased cloudiness which decreases downwelling shortwave radiation. We looked at this just now in Arctic amplification process where these are going on. We also found that more than 70% of the extreme hourly temperature anomalies occur in the mid-latitudes in atmospheric rivers, many more than would be expected by chance alone, which means the atmospheric rivers are increasing the probability of extreme temperatures at hourly time scales. Okay, what are the implications? It was already well known that atmospheric rivers make up most of the atmospheric moisture transport in Earth's mid-latitudes, but our results indicate that they play a much larger part in global energy transport than was previously recognized. We also found that atmospheric rivers are associated in many regions with a substantially increased risk of moist heat waves, which are particularly dangerous for human health owing to the combination of high heat and humidity. This finding suggests that taking atmospheric rivers into account could improve the ability to predict potentially catastrophic heat events. And atmospheric rivers have advective timescales, and you can see them coming. For obviously gives you predictability there as well. It's also possible that the effects of atmospheric rivers on surface temperatures are even larger than we estimate. Our conservative method does not capture the effects of water vapor that lingers in the region after a storm dissipates, and this could warm the surface even further. As the world warms and the atmosphere is able to hold more water vapor, atmospheric rivers could become larger, stronger, and more frequent. In general, warm atmosphere holds more water vapor, and then dynamics can give you more atmospheric rivers. Our next step is to determine how temperatures in atmospheric rivers change over time, with a particular focus on the extreme temperatures and moist heat waves that are so dangerous to human health. So let's look at a figure first and then come back to expert comments and so on. So these are the temperature anomalies, the influence of atmospheric rivers on air temperature anomalies and extremes here. Annual mean temperature anomalies measured 2 meters above the ground in atmospheric river events. So it's a composite, and you can see even polar regions have substantial temperature anomalies related to atmospheric rivers. Greenland, for example, you know there is accelerated melting going on and all kinds of positive feedbacks with melt ponds and moulins and glacier sliding, so on and so forth. So polar amplification is aided by atmospheric rivers as well, but mid-latitudes here are dominated by atmospheric river related annual mean temperature anomalies. Risk ratio of extreme temperature anomalies during atmospheric rivers. A value of 5, for example, indicates that it is 5 times more likely for an extreme temperature anomaly to occur in an atmospheric river than would be expected if the events were independent of atmospheric rivers, which means how the atmospheric rivers amplified the extreme temperature anomalies. Okay, so you can see that there are numbers of 9 and more even in Sahara and on the oceans in many places where this is where the ITCZ, well, it's over here, but this is where you have lots of atmospheric river, winter precipitation, etc. And this is quite deep into the tropical latitudes here, not just mid latitudes, but you can see the risk ratio here jumps quite high over Greenland, Arctic, and also Antarctic. This is obviously not good overall for glacier melt, sea ice melt. In fact, I'm going to report a paper which says that the sea ice loss in Antarctica is actually increasing heat loss from the Southern Ocean and driving storms across the planet. You know how far these influences go, right? So what is behind this paper? I won't read the details, but it can just be summarized here from the editor. This is from the authors themselves. The main effect, I think it is from the authors, it doesn't matter. I have actually cut it off here. That's not good. Anyway, the main effect of atmospheric rivers is obvious. Huge amounts of precipitation over short time periods, but sometimes with catastrophic impacts. However, such obvious effects can obscure subtler but nonetheless important processes. In this paper, Schultz and Laura find several ways in which atmospheric rivers can alter the composition and dynamics of the atmosphere, revealing surprisingly large control over extreme events. Okay, what does the expert say? This is Kyle Mattingly at the University of Wisconsin, Madison. The opinion is fairly mild. In my opinion, this direct association between atmospheric rivers and warm temperature anomalies causing potentially hazardous heat waves and other societal impacts is relevant to both atmospheric science community and the residents of the affected areas. Not a very glowing endorsement, but some people tend to be less exuberant about things in general. Let's just read the abstract of the main paper by the same authors that gave the summary here and the conclusions they draw as well. Atmospheric rivers cause warm winters and extreme heat events. Atmospheric rivers are narrow regions of intense water vapor transport in the Earth's atmosphere. These transient phenomena carry water from the subtropics to mid-latitudes and polar regions, making up the majority of polewards moisture transport and exerting control on the precipitation and water resources in many regions. In addition to transporting moisture, atmospheric rivers also transport heat, but the impact of this transport on global near-surface air temperatures has not yet been characterized. Here we show that seasons with more frequent ARs also have warmer than average temperatures in many mid-latitude regions, and that AR events are associated with extreme temperature anomalies of 5 to 10 degrees C above the climatological mean. This is due to anomalous horizontal transport and convergence of sensible heat and moisture in the lower atmosphere, which increases both downward sensible heat flux and upwelling long wave radiation at the surface. On an hourly time scale, over 70% of extreme warm temperature anomalies occur within ARs in large portions of the mid-latitudes, and ARs are associated with moist and compound heat waves in many regions worldwide, suggesting that consideration of ARs may improve predictive capability of certain extreme heat events. Our results demonstrate that ARs significantly impact air temperatures on a wide array of timescales, and that they may play a wider role in global energy transport than previously recognized. Downward sensible heat flux basically means that the surface is cold. All these atmospheric rivers are bringing very warm air near the surface at 2 meters, which means the heat flux is not a loss from the surface, which tends to be more typical, but especially over the ocean, because ocean tends to be warmer than the atmosphere in most regions. But here, atmosphere is warmer, so it is putting heat into the surface, which is what can produce extreme heat events, right? I'm skipping all the figures. There are some nice figures that you can go and look up. what are the conclusions? Atmospheric rivers have significant impacts on near surface air temperatures on multiple time scales, from seasonal averages to hourly extreme temperature events. So there is a low frequency rectification, in the sense that atmospheric rivers are not like actual rivers on land, which are flowing all the time, even though they may have seasonal ups and downs, but most of them are alive all year long, whereas atmospheric rivers are transient events that happen once in a while in a season, especially in the winter, but they can bring so much heat that they actually alter the seasonal mean temperatures as well. ARs cause warm near surface air temperature anomalies across the mid latitudes and polar regions, and the majority of extreme hourly temperature anomalies across the mid latitude storm tracks occur within AR features. These warm temperatures result from anomalous transport and convergence of sensible heat and moisture in the lower atmosphere, which affect both turbulent and radiative surface heat fluxes. Although the dominant role of ARs in polewards moisture transport is well understood, the large anomalous transport of sensible heat indicates that ARs also play a critical role in polewards heat transport. They keep saying polewards, but editor didn't catch it. I guess I would say poleward heat transport, not polewards heat transport, but anyway. I'm not a native English speaker either, so what am I complaining about? It's possible that temperature effects associated with ARs are even larger than those estimated here. Our conservative method of determining AR association depends strictly on the spatial bounds of the identified ARs. However, the case study of 2021 Pacific Northwest heat wave showed that lingering effects from an AR impacting Southeast Alaska worsened the ongoing heat wave in the Pacific Northwest far from the initial landfall location. So AR made a landfall somewhere, and then the moisture effect spread over the Pacific Northwest. It is therefore likely that areas surrounding the identified ARs could also be impacted by them, and that the effects might remain for some time after the ARs have dissipated. There may also be other mechanisms that cause temperature increases during ARs. Recent studies showed that ARs may carry sand, dust, and other particulate matter if they pass over regions like the Sahara, further intensifying the trapping of long-wave radiation and creating potentially dangerous conditions if they occur in the summer. Well, this is extending the argument a little bit, but I'm sure they'll follow up whether this is possible or not. And there is a reference for that you can look up. Further study, that will be more on the summer heat waves. Further study of the relation between the ARs and heat waves is warranted, particularly in the case of moist and compound heat waves with high wet bulb temperatures. As the world warms and the atmosphere humidifies further, ARs may become larger, stronger, and more frequent. How these changes will impact near surface air temperatures and global heat transport will have important implications for the future of mid-latitude climate across the globe. Okay, so the Sahara is shown here. You can see large risk ratios as opposed to the temperature anomalies, which seem modest, but still remember these are warm regions, so you expect the temperature anomalies to be smaller than the cold regions, but the risk ratio is high nonetheless, and if they come in the summer, obviously they can create quite serious health risks and so on. Okay, so again, brief, but I got enough of the salient points covered, and you obviously need to follow up with a paper if this is of interest for you. Alright, see you in the next topic. As I said, I'll jump to Antarctic sea ice loss, ocean heat loss, and global storms in the next podcast, since these are closely related to each other. Okay, see you.